Soumendu, would you like to introduce yourself, and then you can start start your talk whenever, and I'll be making hand signals for the amount of time you have left.
Sorry, may I share my slide then introduce myself? Is that
yes, of course. Yeah.
Yeah. Okay. Okay. One second. Just a second. Yeah. So hello everyone, I am Soumendu Bhattacharjee. Right now I am located in Prague and working at Czech Technical University as a research scientist. Before that I was in Vancouver as at Triumph as a postdoc. So I moved in Czech Technical University on last year July, and I joined there on August. So yeah, that is my very brief story. Right now I'm looking for data science job and I want to come back in Canada. Yeah, so today I'll talk about the fight detection on live stream camera. In the subsequent slide, I'll discuss about the vision-based fight detection from surveillance camera, which is basically based on this paper, whatever I shown. First question comes in our mind, why we are going to detect the fight in the live stream camera? The answer is here. So here I listed. The reason is detection of flight from surveillance camera in public area, prison, etc. is desired to get a quick action quickly get under control of these violent incidents. And violent scenes are common in movie or media. It can be blocked from media or movies so that the young generation will not able to access this. So fight detection is basically divided into two parts. First one is the feature extraction and next one is the classification. The feature extraction, there are two types of feature extraction are available. So first one is the computing of optical flow information of videos, and next one is the deep convolutional neural network based representation. But CNN is the best way to deal with the computer vision oriented problem, and LSTM is used for modeling the temporal information as they find the relationship between the consecutive frames from their memory ability. So finally, CNN plus LSTM network is used for action recognition due to its high performance. To approach this problem, they use a modified exception CNN is trained using the fight scenes. Thus, it is expected that CNN is more familiar with the input sequence and extract the more relevant features from them. In the classification section, a novel approach is developed by using LSTM, and along with the self-attention layer is used to improve the performance. In the feature section, two types of CNN architectures were tested for this feature extraction part. First one is VGG16 and next one is exception. VGG16 is basically which takes the 224 by 224 pixel resolution image as an input, and it has three fully connected layers at the end. The features are taken from the second fully connected layers. In the exception side, it took 299 by 299 pixel resolution. The features are extracted from the last global average pooling layer. In addition, the fight CNN was used for the fight detection. Fight and non-fight frames of the video sequence in the hockey dataset were used for training. The trained CNN has exception architecture, but the last layer is mapped into the two classes. The kernel size is widened in order to catch the more relative features from the fight scenes. The new network with exception is smaller than the regular model, which is basically 11 million parameters. It has also two fully connected layers before the classification layer, as features are extracted from the first fully connected layer. Before sending the videos for the feature extraction, the frames are sampled from the video sequences. Uniform sampling was used. 5 and 10 frames from the each videos are selected. Then a cubic interpolation was used. These frames are resized and an input size of the network architecture. Here I present the flowchart of this methodology. Before the samples sent into the feature extraction, the videos are sampled into the 5 to 10 different frames. And then in the feature extraction side, VGG 16 and exception were used. And in addition, fight CNN was also used in this process. In the classification side, the by LSTM along with the attention layer was used in this proposed system. In the classification side, by LSTM is used since it can learn the dependency between the past and current information. After completing the forward learning, a backward learning is processed starting from the last element to the first element. Therefore, each cell, both the past and future information is kept, and output are determined by taking into account from the both of this information. The by LSTM, the same architecture. By LSTM is basically the same architecture with the regular LSTM is used with an additional by LSTM layer instead of only LSTM layer. The dropout is applied in order to reduce the overfitting. In case of attention layer, it is used in the visual problem in RNN for deciding how much attention is required. Attention layer plus by LSTM computes the weight for each cell to interpret each element in the sequence. Attention layer determines how much each output should be affected by other inputs. After observing the past and future information, it generates a weight matrix, and that matrix used to calculate the outputs. In the experimental results side, the 5 specific datasets were taken from the hockey games and pelliculus dataset and surveillance camera dataset, but the major contribution was from movie and hockey games. There are few challenges are involved to detect the fight from the surveillance camera, which is basically they mentioned the hockey. For example, in case of hockey games, the background of the videos does not change much. In case of surveillance camera, the human in the scene and the background of the images differ for different cameras, for example, bar or some restaurant or some other places. In case of the movie and the hockey game cameras, background is moving due to zoom in and out, but surveillance camera background is more or less stable. So basically stable. So only surveillance camera dataset can solve that purpose. So here is the.
That's it.
Oh, okay. So sorry, I didn't notice your warning. So here I just present the result. So we can see there is the accuracy is not great. So which is basically because they mention in the data set there are high number of in the variety number of samples in the data set is quite high. So that is why they are not able to fit the data set properly. So that is why they are not able to achieve some good accuracy. So here is the conclusion. So yeah, you can.
No, go ahead. Leave it up.
Slides.
We're just going to do Q&A, right? So yeah, just leave it up so people can read it. Yeah,
this is the conclusion. So
yeah. All right, thank you. Does anyone have any questions? Actually, like I will start. This is one of the nice things about being the organizer is I'm curious about. So it sounds like you had a lot of stuff from like fights and movies. Sorry, not fights and movies and hockey. I'm
Mhm.
wondering are there other data sets besides the surveillance data set? Because my worry is that the fights in movies tend to not be very realistic. Are there other sort of like proxy data sets that you also considered?
Yeah, actually, they fit with some other data set. For example, in case of this pelliculus data set, they got some nice accuracy. And similarly, in case of hockey data set, they also get some nice accurate result. But when they are applying this in case of surveillance camera stuff, it's not working very well because of this. This is roughly 70%. So they claim that there are different types of movement are involved in this surveillance camera data set. That is why their model are not able to generalize that. So that's what they are claiming. So that is why they got the 70% accuracy.
Can I ask question?
Yeah, and then Bruce.
How big was a test data set?
Okay, just a second. I think I took that slide somewhere. Yeah, this is their number of samples for this data set. So
it's so small.
Yeah.
So and all those what percentage of data with fights and without fights? It's a two-class classification, right?
Mm-hmm.
Yeah.
So sorry. What is your question? I didn't.
The question is what percentage of data with fight and without fights?
Oh, yeah. You can see from
okay.
here. Yeah, from
Fights
here. This
okay,
is,
got
yeah,
it.
yeah,
Got it.
yeah.
Sorry.
So yeah.
And Bruce, I saw your hand.
Yeah. Yeah, I actually put my hand up. I'm so good. So it seems the applications that people would have in mind for this, if it worked, would be things where you'd want in real time to be able to detect that a fight is happening. But
Yeah,
a lot of these techniques use future data to make a judgment about what's happening. So why?
Means can you say that again? What are you saying?
Well, I'm curious about why so much attention was being put on these techniques that use future data, like a bi-LSTM. It starts at the beginning and it also starts at the end. Whereas the intended application is one where you need to be able to detect a fight in real time as it's happening, right? In which case you could only use past information. So I'm just curious why so much attention on non-causal models, basically, where they use future data.
So yeah, you mean that that here you can see that if when they add this by LSTM, it's actually they said that if they're adding this by LSTM, they're getting better result. So compared to LSTM, it's that
I'm sure they do, but if the intended application is to be a real-time detection of fights,
I don't think they mentioned something about that. So in that paper, so yeah, but I don't think so. Sorry.
And imagine another application could be if you have like 10 hours of surveillance, you're looking for a fight, you sort of look for it like that. I mean, maybe it's not super useful, but
yeah.
This also seems like it is pretty close to real time, even if it was using a by LSTM though. Like the 10 frames there, I'm sort of interpreting that as being like the the actual sample size, which is it's about half a second.
That's a good point. Yeah, so a delay of that long is not going to be a big deal.
But
It is
also
kind of
sort
remarkable you
raises
can
the-
get some good classification just off 10 frames of data.
Yeah, it doesn't seem like very much to me.
So are the videos 30
It's-
frames per second?
Yeah, they sample this video in this two set 5 and 10, but 5 and 10 results are not way different, because this is the result. You can see that it is 71 and 72%. This much is the difference.
It's still good result.
It's interesting that 5 frames is even better.
Yeah, in some cases, yes. Yes,
If you go to 1 frame.
But again, I'm not sure, because their data size is not that big. So how good that result is, I'm not sure.
Did they, since they were using such short frames, did they consider using like segmenting parts of the fight into different like training examples? Because if you're only using 10 frames, then in principle, like you could just pick half-second segments of each fight and then use that as a training data point, and that would significantly augment the size of your data set.
So they're uniformly sampling the frames, is what I understand, from the entire movie, right?
Just a second. Let me pull out that paper.
So in your slides, it says they're uniformly sampled. In the diagram there? Uniform sampling?
Yes.
Yeah.
Uniform sampling, yeah.
So it's not just a really short clip. It's pictures spread out throughout the movie.
Pictures spread out as in non-sequentially? Is that what they mean?
I think like it's a downsampling, right? But it's still in order, right? So I would guess that it would be like a very choppy GIF is what the actual training is going to look like.
Okay, that seems like an odd choice.
Yeah, no,
That's
it does.
I mean, in a sense, it's a bit like using a diluted convolution, but I mean, still an odd choice.
Yeah, and actually brings more to Bruce's point. So this is probably something that you would have to do. But I think I saw something in your appendix notes about a streaming version of this, but I'm not sure.
Me?
Yeah. I'm not sure. I just very quickly looked over it.
I don't think so. This is something, no.
Is that the paper though? If you could go back up, the one with the abstract.
Yeah, actually, just a second. Which one is the?
Yeah,
No,
that
this
one.
is different. No. This is something different paper. No, not this one. So I talked about only this paper, not mix up between 2 or 3 papers. So just this one I talked about. Yeah, I send you this paper.
Yeah. Which I will go post the link to in the chat. I have one more question, and then we're gonna have to jump to the next one. This is from the chat. Did you consider audio features, assuming fights would have clear audio? That might help. Yeah.
No, they didn't mention anything about the audio feature. No.
All right. Thank you for the talk. I'm gonna go clap. People, if they want to unmute, they can unmute. But it's always hard to clap over Zoom. But thank you for giving the talk. just by the way, he's giving this talk at 3 a.m., which is an incredible amount of dedication. So thank you so much for presenting. That was really great. All right. The next speaker is me. So just give me a second here. Is this just the presentation by itself? Ooh. Hello?
Yeah, looks good here.
Okay, and then I'm going to bring up my speaker's notes. Rid of that. And this. Can anyone see my speaker's notes?
Nope.
Okay, awesome, great, perfect. Yeah, so just a quick introduction about this. Oh, I guess I should also say who I am. Hey, my name is Matt. I'm a senior data scientist at Roblox. I work specifically in something called assessment tools. So I build game-based assessments that try to measure problem-solving ability. This talk is not really directly related to anything that I did there, but it was an idea that I sort of had while I was at work, did not work on the thing that I was working on at the time. And then I kind of more fully fleshed it out a little bit later. And what I have for you today is what I think is it's a pretty neat hack. I'm not going to say that this is like a major research result or anything like that, but I had never heard of it before I like started like trying to build this thing out. So yeah, this talk is about explainable outlier detection. I have all the code. So this is done through a Jupyter Notebook. All the code is available for free from that link. And if you can't get it from here, just go tell me and I will go post it in the chat later. All right. All right. The other thing I got to do is I got to give myself a time limit as well. Okay. Yeah, so the title of this talk is called Weird But Why Explainable Outlier Detection. So before we get into outlier detection, we got to discuss what an outlier is, and this is actually a surprisingly subtle point. So what we're seeing right here is several outliers, P1, P2, P3, P4. You'll notice that P2 is actually a cluster of outliers, and that is also interesting in of itself because depending on the context, P2 might be something very important that you definitely need to include, or it might be some artifact of noise, and we're going to have to try to figure out what are these two things that actually is, and that's kind of part of what WinTalk is about. Outlier detection is the sort of collection of algorithms that are used in order to try to determine what is and what is not an outlier. This is from the PyOdd package, which is essentially the reference outlier detection package in Python, very similar to scikit-learn. One of the important things to know about outlier detection is it is typically an unsupervised learning method. And that means we don't have any labels, and we're just kind of going off of essentially what these distributions look like. Although sometimes it can be used as, there are some like self-supervised algorithms as well, but I'm not going into that today. So the example I'm using is from a benchmark data set called odds. This is just used to sort of to benchmark new algorithms, but this is one of the smaller data sets. This is called the Lympho data set, which is about lymphography, which is essentially like an old way of diagnosing lymphomas before we had PET scans. And the data set, quite small, is 148 patients with 16 features of these lymphograms. And then there are 6 outliers, and these are lymphoma cases. So right now, just to put this into your head, you could also imagine this as an unbalanced supervised classification problem, right? But in this case, it's going to be unsupervised. And here's just what that code looks like, pretty simple to work with. What does the data actually look like? So we do a PCA here, and we look at the first 2 principal components. and we see, oh, there's a nice clustering of data points here, but there's also a few data points here and around here that look different from everything else. So if we were to guess where the outliers are, remember that there are 6 outliers, we would probably say, oh, these 4 and maybe 2 of these over here. But in actuality, we have the 4 that we expected. We have 1 over here, which makes sense. But if you look very carefully, there's actually a little green guy right in the middle of this cluster. So that actually already tells us something about what this data set is like, which is that 2 principal components are not enough to actually fully describe what is and is not an outlier in this data set, right? It also suggests to us that although PCA can be used as an anomaly or an outlier detection method, it probably won't work so great in this particular case. So what are we going to use instead? There's something called an isolation force, and it's a pretty smart idea. Essentially what it says is outliers tend to be separated out from everyone else. They tend to be isolated much faster than the typical data point, right? The way that I would think about this is if you're doing a game of 20 questions or guess who, right? And you ask a single question and it removes everyone except for a single person, that probably means that that single person is an outlier in some way. Now, the technique used here is something called an extremely random forest. So that means that you have all the trees in a random forest, which are already quite random, and all the decision points are also random, right? So everything is completely random, and we just see what is the average path length or the number of decision points before a data point is completely isolated. Okay, how does it perform? Shockingly well. I swear I did not manipulate this. This actually is like the perfect classification. You have to remember, though, that outlier detection is unsupervised. So I did give this method a little bit of a hint where I said that the contamination, which is the percent of data points that we think are going to be outliers, is 4%, which is the true amount in this case, right? If we did not have this, there would just be a little bit of guessing and there'd be more false positives. But it turns out that isolation forests are very powerful, especially on such a simple data set. Okay, explaining outlier detection. This is great. We have this isolation forest, but we have no idea what it actually means. We just know that, or we think that these things are outliers, but that can mean really anything. What we have to do is we have to come up with some sort of explanation for why these things are outliers. And then on a case-by-case basis, we need to go down and we need to say, okay, is this thing an outlier because of something intrinsic to the data? Or is it an outlier because of some artifact that is not intrinsic to like the thing that we're trying to model? So a great way to do this is something called SHAP values. SHAP values are essentially, Shapley values are a game theoretic idea, which essentially is trying to look at, okay, how many, how much does an individual player add to a team, right? So imagine like an NBA player, if you were to remove that person from the team, right? What would be the average number of points that you would score in a game, all other things being equal, right? It turns out that this is a really computationally expensive thing to do because you have to look at not only every single player, you also have to look at every single, every single combination of everyone who is around. This can also be applied to, in a machine learning context, only instead of having players, you have features. And we're going to see that right now. I am running out of time. So this is a typical case. And remember that the sort of SHAP value that we're talking about here, the average, which is a 0, right, would be a path length of about, let's say, like 9, right? And all of these different features are actually adding to that length. So we have 0.21 for the first feature and 0.2 for the next feature. That's making the path length larger. That's making these things more typical. Now we have this outlier here where we have several different things that are all saying, oh, this thing is an outlier, right? This would suggest to me that this isn't just one, there we go. This isn't just one thing that's going wrong. There are several things that are, there we go. And that there are actually several things going wrong that are making this thing an outlier. And this is actually a true data point. This is not just noise from a single measure. That's my talk. Okay. Q&A. I can't see everyone. Let's just start talking to me because I actually can't see who's raising their hands.
Can you increase the font size for the bibliography? It looks tiny.
Yeah, let me go do that. I can also, I think I have like the full BibTeX bibliography as well. I should say that in here, while I was researching this, I found a single like blog post of someone else who found this out in like 2017 or something. Where is that? Yeah, this one. That I think it was accessed. Oh no, yeah. So this was actually from November. So actually, I think we had the same idea around the same time. This is actually, that's actually a pretty nice blog post going into more detail about what's going on here. There's some other nice stuff as well here. Differences a brief overview of outlier detection techniques is nice for like an introduction. And then there's also there's actually a textbook in here for explainable AI, which is quite good as well. And that's completely free and open. So I would highly recommend that as well. But I can't find it right now. Maybe it's not in this, it might be this one. Yeah. Okay, anyone else have a question?
Matthew, can I ask, is this method, I mean, my understanding of isolation force is that they're better for low dimensional data. Do you have any comments about the dimensionality, where this is appropriate, and what other alternatives if you're in another regime?
Well, that's interesting because I heard that it's actually more for high dimensional data. The problem with a lot of other outlier detection techniques is they rely on some sort of intrinsic sense of geometry. So you see a lot of like nearest neighbor type algorithms. And if you have different features that are, say, you know, like all the features here are like categorical features, and it works really well there. I would assume that this would actually scale quite well with a high dimension. If that is not the case, there are also like gradient boosted tree versions of this that like I think would work even better with a high amount of features. But I don't see why this wouldn't work well with a low cardinal with a high cardinality.
I mean, let's say you had a bunch of images, and
oh yes, okay.
one was an outlier, and then maybe there's only one image where the top left pixel is light green, and it would be easy to.
Yeah, in that case, I would definitely not use that. There's actually a SHAP algorithm that works specifically with neural network activations that's not covered here. But this would be more for tabular data. But yeah, I would definitely recommend. There are also, to be honest, I don't understand how the outlier detection for neural networks works. This is separate from like those attention masks that you've seen. But there are definitely neural network algorithms that do outlier detection, and there is like a SHAP assumption that you can make that works with neural networks as well. So I would look into that.
Thanks.
Matt, I have maybe a super basic question just in general. Like, so I guess it's implicit when you say an outlier that most of your data is in some cluster or some distribution, and then there's a few that's away. Like, is that kind of used in these algorithms? Is that fact? Like, if you have a bimodal distribution and you run this, are you gonna get one of the peaks to be the outlier?
Yeah, so you can definitely have that happen. And like, this is why you have to be super careful, and why I recommend that anyone who is actually attempting to do outlier detection think very carefully about why they're doing it. The case that I was looking at was like a cheating detection type thing. But what I kept on finding was I wasn't detecting cheating. What I was detecting was someone interacting with a game in a really weird way, right? Like, so you wouldn't want to use this algorithm for that, right? There was actually like a really great, I was going to end the talk on this slide, but I already knew I was going to be over. But Andrew Gelman had written like a little comment in 2014 about how outlier detection is something that like non-statisticians think that statisticians do, but we don't. And essentially what he was meaning was people just assume that you can make a box plot and you say, oh, look at there's some values that are out of like the normal like quartile range, and I'll just remove those. But like, you should not be doing that. What you should be doing instead is checking to see, oh, I have like this value that is way out of what I expect. Is that because of, say, sensor noise, or is that because we have something real here that just is so rare that has not shown up before. So yeah, like going way back to that first slide, you see a little small cluster. And I would say those probably should not be considered outliers at all, and probably should be included in whatever analysis that you're doing.
Okay, thank you.
Anyone else? I got about a minute left.
I have a question.
Question about your explanation of isolation forests, because
Sure.
I love the concept. I just couldn't really get it that well.
Yeah.
If the decisions are random, but they are among things that decide in that space.
Mm.
Like you can, if you just take completely random decisions, you can end up with everything in one node. So
Yes. Okay. Yeah. So with the constraint that at least one data point will be separated, right? So
Great. Okay.
you can imagine that there'd be a cut of like temperature is below absolute zero, like that. Like it's a uniform. I believe it would be a uniform random, but with the min and max of the data set.
Perfect. Thank you.
There was one more question. Was that Nicole?
Yeah, I had one. This might
Yeah.
be a naive question, but I'm going to ask it anyway.
No naive questions.
So you mentioned that this is an unsupervised problem, but also that we know that there are 6 outliers. And so how do those two things square with each other?
Yeah, so if you were to use this in anger, you would absolutely not know that those were 6 outliers, right? This is purely as a benchmarking demonstration. The way that I was thinking about this is when people measure, like, say, goodness of fit for, like, you know, like, let's say like a mixture model or something like that, or some sort of dimensionality reduction. And the way that they do that is usually they generate some sort of synthetic data set from like a known distribution, and then they try to fit it and say, oh, look how close it was to fitting, you know, the synthetic data set. It's exactly like this case here. Like I could have made my own version of this where I knew, okay, there's going to be 4 data points, but you know, this one was real. It's used as part of like a benchmarking tool, but like, yeah, do not expect to know what the amount of contamination is going to be when you're actually using it.
Gotcha. Thank you.
All right. That's it. Nicole, you're up next.
Okay. Thank you, Matt. Let me share my screen. Can everyone see presentation screen? Okay, thank you. Perfect. Hi, everyone. My name is Nicole, and I am based in Vancouver. I completed master's degree program in management analytics at Queen's University last year, and I am currently studying in the professional data science program at McGill University. And in order to going into data science career trajectory and for further training, I will be doing intensive data science bootcamp at Lighthouse Lab for the next few months very soon. So that was my introduction. To begin with my presentation, let me ask you this question. How would you improve the online shopping experience of customers when browsing the entire merchandise through mobile handset is challenging? Based on a 2017 business case of Big Basket, I will be presenting the customer analytics and recommender system. So what is Big Basket? Big Basket is India's largest online supermarket. It has both the online platform and app that can be downloaded from app stores such as Google Play. Big Basket primarily targets tech-savvy young working generations, and it currently sells over 20,000 products to 100 million customers. The company adopts the online grocery delivery business model that works by purchasing farm products and home essential items, managing them in its warehouse, and distributing to its customers. Big Basket's issue with high operational costs and reduced profits were closely linked to poor customer online shopping experience due to lack of predictive analytics. For example, for the small set of regular items, customers had to scroll down to go through a sea of products on their small handsets, spending 20 to 30 minutes to place an order. No efficient recommender features caused higher delivery costs due to multiple deliveries from its warehouses to customers per day. Loss of customers and smaller basket size order also resulted in reduced profit. So as a solution, 3 analytics features were proposed. And with their implementation, it was expected to enhance the customer's online shopping experience, thereby increasing the customer's average order size and the efficiency of the operation. Market basket analysis was the starting point of analytic work, and I mainly use R and Tableau. First, I worked on transforming data, starting with the data pre-processing and converting data to transactional data to further study the existing rules. I studied the item frequency in transactional data by observing the absolute and relative item frequency plot as a groundwork for building recommender systems. And I observed the density of this transaction object and generated rules using a priori function. These processes comprehensively led to the 3 types of recommenders: top 20, smart basket, and did-you-forget engine. The association rules are the rules extracted on item sets from transactional data through the association rule mining and a priori algorithm with the core elements of support, confidence, and lift. These rules exhibit the relationship based on the influence on frequently co-occurring associations among transactional items. The diagram illustrates the algorithmic process of driving the association rules. So Smart Basket recommender features was created through association rules, and based on the Big Basket's data, I extracted total 194 unique rules to create Smart Basket. Then these rules were ordered by the highest lift value to find the most influential recommender features. Afterwards, I closely studied the association rules and other characteristics and top 5 rules by generating various rule-based visualization. How did I extract 194 rules for Smart Basket? In step 1, I plotted the density map with 0.43% density. In step 2, I plotted the line graph that showed the number of rules that could be generated on the varying degree of support and confidence. In step 3, based on the ranging number of rules between 0.1% and 0.3% support levels, I determined the optimal number of rules with 0.25% support value and 80% confidence that generated 248 rules, which were further reduced to 194 rules by removing the redundancy. The association rules in a Smart Basket are like an interactive network, where each rule has its unique association with items and with other rules. Each rule consists of left-hand side items, which are what customers picked in their shopping basket, and right-hand side items, which are what the Smart Basket feature is recommending based on left-hand side items. The other recommender feature, Did You Forget, was developed through the item-based analysis, where Recommender Lab R package provided a framework to evaluate and compare 5 different recommendation algorithms and quickly establish the best suited approach using cross-validation. ROC performance matrix with TPR and FPR plots were used to select the optimal recommender. This slide illustrates how the optimal recommender was selected based on ROC performance matrix. So now moving on to scenario analysis of Smart Basket and Did You Forget recommender engines. The Smart Basket recommends items to customers through the recommendation notification pop-up, which shows top 5 rules associated with this customer order. The items with the highest lift value in a Smart Basket would be our top recommenders. And out of these items, I found that the brinjal, the Indian eggplants, and cream biscuit had the highest lift value. So what does this mean? Brinjal, the right-hand side item in row 1 and 2, are associated with onion flour, bottle pickles, beetroot, broccoli, and haricot, which are left-hand side items. As the left-hand side items are more likely to determinant factors, I can recommend and tell customers, hey, people are also buying brinjal. Would you like to add it to your basket? With the cream biscuit, we have cross-selling opportunity. 2 green biscuits are in row 3, 4, and 5, but with different flavors. As the orange flavor cream biscuit is a determinant factor for all the rows, customers will likely buy mint flavor cream biscuit. So we can recommend customers to add the mint flavor cream biscuit to their basket. Did You Forget recommender is activated at checkout and suggests top 5 items that may have been forgotten based on the basket content. So how this engine works? Imagine that a customer is online shopping for masala recipe. In the basket, this customer adds organic masala and other sauce. At the checkout, Did You Forget engine is activated. Then it scans the content of the basket, and based on the scanned content, it produces the list of 5 items that the customer most likely forgets. This gives the customer the opportunity to add the items from the Did You Forget list into the basket before customer proceeds to payment. Based on the discussion so far, we can envision what the new customer order process should be. Customers log in online, get the prompt to see if they want to start with top 20. If yes, then they start with top 20 and proceed with online shopping. As they continue, the smart basket system recommends items based on their association roles and purchase history. At the checkout, Did You Forget recommender is activated to scan the content of their baskets and comes up with the list of 5 potential items that they may be forgetting and give them one more opportunity to add those items into their basket before they proceed to payment. So this is the end of my presentation. Thank you very much for listening, and I will open the floor to questions.
Nice job. You finished with 10 seconds left.
Oh, okay. All right.
Mm-hmm. Any questions? I will go start. I'm kind of curious, how long did it take you to do all of this?
Actually, I do have a code that I had to use on the actual Big Basket data. So it took me a while, actually. It took more than a month. Actually, this was my team project in my master program last year, and I was a team lead for that team project. But I mainly worked on creating a recommender system, and I helped on the Did You Forget recommender engine as well. So I had about like the data that range about 1 million observations. And then I had to create a transactional data that ranges about 500,000 to 700,000. And then that was a starting point to do all the analysis.
Can I ask a question?
Sure.
What would you do next? Oh, thank you for the talk. And I'm wondering, what would you do next if you had a whole bunch more time?
I would I would drill down on, I will show you a brief visualization here, which would kind of link to what my next step would be. So this is another graph that showcase regarding the Did You Forget recommender engine. And this one actually, and then with other ROC curve with the TPR and FPR plot, evaluates on the 5 model that was used. So I will actually drill down to each individual model and kind of make analysis as to what the trade-off and what the efficiency of using each machine learning algorithm to come up with a better Did You Forget recommender system.
Cool, thank you.
I have a question.
Sure.
So the association rules and the Did You Forget something? Those are 2 separate models, is it, or are they the same?
Yes, they are functionally 2 separate models, but they are based on the same principle and rule, which was based on the association rule, which was pulled from the a priori algorithm. And then what happened is, this is the slide that I didn't get to share, but those 2 systems stemming from the same process in the which was used based on the association role mining, which has these component. So the first will be a sub-2 test that's associated with the association role mining, which is equivalently the market basket analysis. And then it will go through the a priori algorithm principle and then rule generation using this algorithm, which was specifically set by core elements of the a priori function, which will be support confidence lift. So, but the only difference in the Did You Forget engine is that it utilizes a machine learning algorithm as well to evaluate the best performance to really pull the most optimal items to the basket. So that's the only difference, but the ground principle, underlying principle is the same for those 2 recommender systems.
I see. Could you speak a bit about how did you structure the data to train the a priori algorithm? Like, was it just pairs of items in each cart, or like just removing one item from a cart and then just iterating through the whole cart and creating multiple rows?
Sure. So what happened is in the general process was following the sort of similar analogy of the process of machine learning model, developing the machine learning model. So that was those are kind of the general process I follow. But in terms of dealing with the data to come up with the rule, association rule is basically based on the raw data, then I have to convert that to the transactional data. That's the starting point of pulling the rule, because a priori algorithm uses transactional data, not the raw data. So in the data pre-processing stage, I will convert the transactional data first, and then using our programming language, I will use the A rule package and read package in the R package to further create the rules. So in the setting stages, first of all, I have to observe the item frequency because most frequent item will be then used to create the rules. So I will do a whole bunch of visualization using R. And then based on doing a visualization, then I will look at the item matrix, which is the base for creating density plot. I have another slide that kind of showcases what the density plot is, which is part of the process for creating the association rule. So this is the kind of overview of what the density plot is. So transactional data is actually, it's like an item matrix. So then I have to also see, okay, how sparse the data is within the item matrix, and then what's the pattern in the transaction, because it also impacts the nature and characteristic of the role that I'm creating. So first of all, I'll look at the density, which will tell me the sparsity of the data. So based on the density, then I will use the core elements of a priori function, which is the support, confidence, and lift. And then I will apply varying degree of support and confidence, first of all, which is the part of the a priori function, and create a plot something like this. So going back to my slide here. So this one, with using the varying degree of support and confidence, then I will pull the different graph, which will show the varying number of rules that was created at the different level of support and the confidence. The most important thing here is that the confidence level should be high, because that will impact the accuracy of the rows and quality of the rows that I'm creating. And then I will test out each varying degree of support and then create different graphs and then determine what would be the number of rows that I want to create. And then that will be my base for setting the fixed support level and the confidence level. The rule of thumb that I followed in doing so was, first of all, I don't want to create too many rules, because that will not help me learn the unique characteristic of the association that exists in the items. And I don't want to pull last number of rows, because then that would not capture a dark web characteristic of the association that association rule that would exist in the item. So that was kind of groundwork. Then once I pull the rule, then I will going into detail of each rule, make sure that each rule makes sense and that it works in function to create a recommender system. So I went through various visualization in studying the association rule. So first one was interactive plot, kind of show you the interactive network. As you can see, this is pulled from the R visualization. And then I will study the group matrix in association rule that I pull. And then I also look at the scatter plot, and I will look at the parallel coordinate plot as well in association rule, and so on and so forth. Like, so I do various things. And then what I do is, based on the rule, once I understand the rule, then I will look at the individual rule, which will be a unique basket that the customer will purchase, and I will study the scenario, which I sort of showcase in my presentation. So I will look at what will be the scenario for each role. And then so I did that for the Smart Basket. Did you forget engine requires machine learning? So I'll apply machine learning and then make sure based on the different machine learning algorithm, what item will be pulled to inform customer that these items are most likely they are forgetting and stuff like that. So that is kind of general procedure that I followed. Sorry, I hope I answer your question.
Yeah, thank you. It was really nice to see those visualizations. So I had another follow-up.
But before that, I got Bruce K and then Leonid.
I'm just curious how you evaluate how well you're doing, like how well your recommender system is working.
Okay, I think that's a great question. So first of all, the only evaluation I can do is on the Did You Forget engine, because I'm actually using ROC performance matrix to evaluate each machine learning algorithm performance. And also through the precision recall curve, I kind of studied the trade-off that each machine learning algorithm is making between precision and recall for each machine learning algorithm and evaluate. So the Did You Forget engine is the one that I could actually evaluate how well the system will be performing and stuff. But for Smart Basket, it's not really easy because I'm not really utilizing the machine learning algorithm and performance matrix. The only way to do so is just to make sure left-hand side item is the right-hand side item, where left-hand side item is what the customer is buying most likely. And then that will be normally determinant factor for coming up with the items that system can recommend. So the right-hand side item, that will be right-hand side item. So then I will make sure whether association that was created between the left-hand side items, the right-hand side item makes sense. And then also another way to check is whether I have redundancy or not. So to make sure that the Smart Basket recommender system has a high quality and it's efficient in its operation, it's functional as well. So then I will make sure to remove all the redundancy, which will have all same confidence level. So that, and I also look at each individual level, study the support level, the confidence level, lift level it has, and then make sure that my role that I pull has the highest confidence level, because that impacts the accuracy of the items that the system will be recommending. And then also I will study the support level and confidence level makes sense and stuff like that. So that's what I will be doing to ensure that the Smart Basket recommender system works well.
That's the end of the Q&A portion. But Nicole, you'll stick around for after the presentation, right? And we can do any follow-up questions. Does that work?
Yes, as I can stick around, and also I have an email on the screen. So if you have any further questions, I'm more than welcome to answer your question through email as well at a later point.
Everyone, go clap. Thank you for the presentation. All right. Next up, we have Robin.
Hi, guys. My name is Robin, as Matthew kindly said, and I am going to present on my simple talk on the evaluation of binary classifiers. Okay. It sounds so simple, right? So with a binary classifier, generally we want to make some decision, a yes/no decision with some kind of model. And if you look at the different steps, generally we have a model that makes some predictions. We have to turn it into this prediction, which is often continuous, into a decision. So we use some kind of threshold, and then we get some kind of cost or benefit from that model. So I'm just going to briefly talk about, classification evaluation is here how we say how's the model doing, how's the model doing in terms of its decisions? And then that requires a threshold, so we have to have some way to pick that threshold. And then we can also talk about, well, is this model really helping in terms of cost benefit? And that's a different thing. We'll take a brief look at decision curve analysis. And then sometimes you really want your predictions to map to probabilities, and that's that would be calibration. So if we look at this upper left table here, this is like a contingency table for showing positive, negatives, actual, and predicted. And contingency table can give you a general picture of how your classifier is performing. But then there's all these other derived metrics that you can use that are listed here. And this is straight from the Wikipedia page. And there's a lot of them. And how to make sense of all these? Which ones do we need? We know if we just use accuracy, that doesn't work too well, right? Like we just have a HIV test that says everyone's negative. That'll be very accurate, but it's not giving us what we want. So one way of looking at these things is some of these measures seem more suited to the patient's view. Like when the patient goes home and gets a positive or negative result, how meaningful is that to the patient? And other measures seem more useful on the aggregate view, like the healthcare provider. How is this model on overall? How are the statistics on how well this model is performing? So you can kind of, depending on what your scenario is or what view you care about more, you might be interested in different types of metrics. And if you look at the common F1, say for example F1 score, and also this one, which I've never used before, but they use only these two metrics. They're combining just these two of all the possible things. And if you look at common curves that are used for critiquing these models, common one would be an ROC curve, and that's using the blue. When I use a blue line, that means I'm connecting these two boxes. I'm saying just these two boxes are used. Just these two metrics are used to create this chart. So this is looking at it with just these two boxes, then you get this chart. Or you could do a precision recall curve, which happens to be just these two, combining these two boxes. Okay, and they have different pros and cons, but if you have an unbalanced classifier, if you have an unbalanced data set, that means like, let's say very few people with HIV, then an ROC curve could be kind of misleading. Like it might actually perform really badly, but still look okay. And then the precision recall curve has the other problem. If the classes are more balanced, or if the negatives are rare, then this might not actually be very helpful either. So it seems like the different charts and the different measures really matter it really matters what regime you're in. Now there's also the total operating characteristic curve. I've never used this one, but it comes up as, it gets mentioned, thrown around sometimes and mentioned as it has a lot of data on here, right? But really what this is like a graphical interpretation of just this contingency table that you have right here. It has all the data and it's in the contingency table, and you can read more things off it, but I kind of find it hard to use. And it's not giving you this higher level analysis like some of these do. So what I like to use, and what gets used sometimes in medicine, is the Matthews correlation coefficient, which if you look at all the terms inside of here, it's actually using 1, 2, 3, 4, 5, 6, 7, 8 different terms, 8 of these different terms, and combining them in one equation. And I like to think it gives you, because it's doing that, it's giving you a balanced view of the performance. So it's not fooled. It can't be fooled by any imbalance, class imbalance. But if you look more closely at those terms, actually the blue terms are just 1 minus the red term. So really it can be summarized by this 1, 2, 3, 4 different metrics. It's combining these in 2 different ways. And you can see it uses the square root. And what does the square root do is it sharpens it near 0. So it's actually more sensitive at 0. At 0, a small change results in a big difference in MCC. So MCC is like a very sensitive metric. And if we look at this, it's also called the Pearson correlation coefficient, or the phi coefficient. And it was introduced back in '75. And it kind of combines the healthcare provider view and the patient view, what I call those two views. But there's some symmetry here. It's saying the positive and negative are treated identically, unlike some other measures that don't treat the positive and negative in the same way. So you may or may not want that. So because there's so many different metrics, some people have tried combining all these different metrics on a single plot. For example, here you can see sensitivity, specificity, positive predictive value, negative predictive value, all thrown onto one plot. And then now you're comparing models by looking at these two plots and kind of looking back and forth. Yeah, I don't know. It's interesting. It's hard to me. It's hard to interpret this. But if you want, you can use the scikit-YB package to make these. I would actually add an MCC to these. I would be interested in doing that. But if you wanted to get back to that initial question of value, the cost benefit, then you actually need another layer, which is the decision curve analysis. And what that does is it says, like, maybe you have to do if you suspect the disease, you might have to do biopsy, and otherwise if you suspect it even more, you might have to just operate directly. And then the biopsy might have some cost as well. Like there might be some inconvenience or cost or health risk to that. And so depending on the ratio here, this cost benefit ratio, you can move up and down this cost curve and decide whether the model is actually helping you in a global cost benefit sense. That goes far beyond just accuracy or any of the metrics we've talked about so far. This is benefit in a different sense. Finally, that might only make sense if you have calibrated probabilities. Yeah, it's my last slide. Thanks.
Nice. Thank you. I guess I will do what I always do and just cut ahead in line. So I'm also a big fan of the Matthews correlation coefficient. Do you have any idea why it's not seen more often? It feels like more obscure than it needs to be.
Yeah, I agree. It seems to be known more in medicine, and I don't know the answer to that. But I think people. I mean, honestly, when I started getting into this, I'm like, God, there's a lot of different metrics, and I just my eyes glazed over. I'm like, well, what do I need to know? So I kind of narrowed it down to So I think it's just maybe familiarity. But even still, like many of these, I'm not really that interested in them unless I know that they're going to provide me some new value.
Gaurav, do you have a question?
No, actually, it was for the Nicole talk, but I can just throw my hand. Sorry about that.
So I wonder, Robin, so the fact that there are so many different things in this table, presumably that's because of those different reasons you want to know these values, right? Different preferences before you even look at these. So you mentioned like patient view versus care provider view. So I wonder if you could compile a set of questions like, do you care about this? Do you want to weigh positive with negative equally? And then based on that, just come up with the coefficient that you should be looking at. I think that would be super useful.
I think that's a great idea, and I think that should be feasible. Yep.
Leonid?
Yeah, my question is, are there some classification metrics that related to big data when we actually could not label a lot of data and make some measurements on partially labeled data? And that's from my real life experience. When you do classification and then you can process part with positives results, but not for negative results, because negative is so huge that you can not actually get false negatives, for example. Never, because it's so resourceful. That's my question.
Why can't you get false negative?
Because you can process classified documents, but unclassified documents, it's not possible because it's a very costly operation, for example.
Yeah, I think I need to chat with you more to understand that question, to be honest.
Okay.
Which I'm totally open to.
Thank you.
I got a question.
And great talk, by the way.
Thank you.
I got a question from the chat from R. What range of accuracy have all the health tests shown? So just to clarify, is this about like the COVID like false positive, false negative rate, or is this about like medical tests in general? Yeah, so PCR and other tests. Do you happen to know this, Robin?
I actually can't speak to that at all. If Ducky's in the room or anyone else who has more information on that, but I would say in general they're pretty bad. That's my impression. Honestly, I think the citizens, the populace isn't really well versed in how much to trust a test. What does it mean if it's wrong 20% of the time? All of this kind of stuff kind of flies over everyone's head, and honestly, even our head sometimes. So I think it's the kind of thing that now citizens, I think, need to know to make sense of what's happening in the world. Any other questions?
So I had a question. So when you get a classification report in the scikit-learn package, it gives you a weighted F1, right? So how does this MCC correspond to like a class imbalance kind of issue?
That's a really good question. I don't have an immediate answer for you on how they do that weighted F1, because they do the macro average and a weighted average. But in my experience, MCC is always more fussy than anything else, any other metric I've found. If a classifier is not doing a great job, then MCC is not satisfied with it. It's so much more aggressive and fussy that I trust it over everything. And I admit I don't think I know the in detail how the F1 score weighted is done. Yeah, but if you look at the F1 equation, I thought it was according to this support. But if you look at the F1 score equation, it doesn't include many of these terms. It's a very simplistic equation, and I think it only takes into account the it doesn't take into account nearly as many factors as the MCC does. So that makes sense.
I see. And this ranges from 0 to 1, the MCC?
Yeah. It ranges from -1 to 1, and it tells you how much predictive value it is. If it's 0, it's kind of like flipping a coin. And only getting +1 is like almost impossible for any classifier. So I'm impressed if my classifiers get up to 0.7 MCC. I'm quite impressed with them. And sometimes that's hard to do, depending on what your problem is, right?
So sometimes you want to bias for like a type 1 error reduction versus type 2. So in that sense, do you like have to do like a MCC above certain 0.5 for type 1 or below something for type 2? Like, is there some kind of interpretation like that?
Yeah, MCC is not biased to either one. It cares equally about both. And but I have thought about making a biased MCC that cares more about one or the other. I haven't tried that. I don't actually know theoretically how well that would work, but it seems like it should be feasible to do.
If I can just jump onto that. So in that case where you do care, like F1 is a specific case of the F beta score, and beta is essentially allows you to weigh how much you care about false positives versus false negatives. If you were to unbalance MCC, it loses this really nice property that Robin already mentioned, where a 0 MCC means there's no correlation between your prediction and what is actually there. And like a 1 is like, this is why I like MCC so much, is it's very explainable. It's the correlation between your prediction and the actual truth, right? So you want it to be close to 1, right? But you would lose that, I think, if you were to weight it, it would not be calibrated anymore.
So what's -1 then? I don't understand how do you get negative values?
-1 is as good as being +1, because that would mean that you would just have to flip the sign of whatever you're predicting, and you would get it perfectly.
Okay, so you should just take the absolute value.
Yeah.
No, God, no. Sorry, my view is no, but Matthew.
Okay. I do remember that, like, I was getting a negative MCC once, and I just like changed the sign, and it flipped over. Let me go check this.
So I've gotten small negative MCCs once in a while on a classifier, and just because that's the best it could do, and it was really sad. And it usually means I don't have enough training data, but it's useful to see that. Like you might get a different MCC on your, it might do better on your training data than your test data, right? And you might see it negative in your test data.
I think it would be nice to see how like MCC varies with the other metrics in the graph that you were showing, that it has like 4 different metrics. And if like MCC was something overlaid on top of that, like, probably
Yeah, I
more easier
agree.
to understand. Yeah.
I agree. I was kind of thinking of maybe adding it to that package, but hey, didn't get around to it. Probably wouldn't be too hard to do. So my goal was to stick within time and to do something that wasn't too super high level like sometimes. So I hope I reached that goal. Thanks for listening, guys.
Yeah, excellent talk. Thank you, Robin. Yeah, everyone do a round of applause. All right. Yeah.
And thanks to you, Matthew, for hosting.
Oh, thank you.